So okay, I'm so sorry for that delay. So today we are going to start with periodic signals. In the last class we discussed about discrete systems and discrete signals, right? So we have x of n is a discrete signal, and this is fed into a function which gives us y of n. This is the other discrete signal. So yn is f of xn, right? Now then we saw properties of linear systems, linear time invariant systems. So today we are going to discuss about periodic signals. Let's say if my xn has periodicity, periodic nature. Last time, if you remember, towards the end of the class, we saw Pratt, and in Pratt, when we recorded our speech, and if you remember, I spoke ah, and this ah, if you zoom into one window, it was periodic, right? So naturally, let's have some dive deep into periodic signals. So whenever we have periodic signals, what is the first thing that you would be interested to know? Time period. So if I give you xn, which is a periodic discrete time signal, how will you estimate the time period of this signal? Any ideas? Pardon? Autocorrelation. Very good. So the first thing which comes to mind is autocorrelation. Okay, let's start from there. So we are discussing periodic signals. Then, what is a periodic signal? This is periodic signal. So now we can notice that if this is my x of n, I've drawn it as continuous, but actually it's a discrete time signal. So if I have my x of n, if I shift it and multiply it with itself, so let's say if I shift it in this direction, let's say, and I get and I multiply pointwise multiplication and sum the two up. So tell me, let's say this shift is L, right? So the product will be something, but as you are shifting further and further, there will be a time when the next period will overlap with this period, right? And at that time, my product will become very large, and when I sum up all these element-wise products, it will really shoot up. Is this point clear? Now I'm moving my signal in one direction, and then my autocorrelation becomes large. So the formula for autocorrelation is RXXL, So here xx means I am kind of taking correlation of x with x itself. So it's autocorrelation. This is defined as some summation xn plus n, right? If my xn is this one, can I say what is the bottom one? What is this bottom signal? Is it xn plus L or xn minus L? Plus L. Everybody is clear with that idea? This is xn plus L. So if I multiply the two point-wise and then I take the sum, now sum will be over what range? N is equal to yeah, generally let's say my original signal was of length n, and I am assuming that the signal is 0 otherwise, like it's a finite signal of support 0 to n, and everywhere else it is 0. To find autocorrelation, my range will be n equal to 0 to n minus 1 minus L. So it was from 0 to n minus 1 because total n samples are there. So n minus 1 minus L, right? And how will this look like? If I plot, what will be my R0? Large value. Very good. It's a large value. Okay. And if I increase my L, this is L. If L keeps increasing, how will RL change? It will? Okay. It decreased. Something like this. Where will this peak occur? At the period. Let's say this period is n naught. Right? Let's say this is n naught period. Then this peak will occur at, this should be n naught. So peak will occur at n naught. Right? What can you say about the height of this peak with respect to the height of the peak at 0? There are two peaks. Which one is higher? Why? Why? Exact? But I'm saying 0 or n naught. Let's say this is synthetic signal with exact overlap. I am saying that my xn is perfectly periodic. It's not approximately periodic, perfectly periodic. Now tell me, out of R0 and Rn naught, or n naught minus 1, sorry, okay. I think I'll make a mistake of minus 1. Rn naught minus 1, which one will be larger? No, it should be n naught only, no? Not n naught minus 1. Okay, just a moment. Let me correct this mistake. Yeah, which one will be higher? Why?
Because more terms you are adding.
Very good. Because more terms are getting added. If my L is n naught, and then you can notice here the number of terms has reduced. Let's say there are 3 cycles in the signal. In the first term, when R is in R0, all 3 cycles they contribute. But in the second term, means R of n naught, only 2 cycles are getting multiplied. So therefore, the total sum decreases. So which means, if I see, my plot will look like this: peak at 0, smaller peak at n naught, even smaller peak at 2 n naught. In this way, the peak is going down and down and down. That's not a very nice property, right? Let's say if my signal had, so if you can see here, there are, within a period, there are, in xn, within a period, there are 3 peaks. So which means, here also, because of these peaks, there are 3 peaks here. So therefore you will also get 3 peaks here. So no, I think I did a mistake. Just a moment. So you will get 3 peaks. Yeah, something like this. Maybe 6 or 3. I think 6 or 3. Okay, we will. Anyways, so basically the point is there are multiple peaks occurring, right? Now, if everything is a decaying thing, then it's possible the first peak is here, second peak is here, third peak is here, and then again. So this peak and this peak, they are in a conflict. How will you decide what is the period? Right? Am I making sense? So it's generally, okay, let's zoom out. So we want to find the period of a periodic signal, and we said, okay, look at its autocorrelation, and autocorrelation will peak at 0 for sure, and then there will be another peak. Pick that highest peak, and that will tell you what is the period. But then we saw another issue that there could be multiple peaks in my autocorrelation plot, and all those peaks, we don't know which one is the actual, which one corresponds to the period of the signal, time period of the signal, right? So let's look at the autocorrelation plot. I can hypothesize that autocorrelation will be very large at n0, and it will be smaller at other points. But then because of this decaying number of sums, that peak, the peak at n0, may be smaller, not because of matching properties, but because of some other factors, that the length which we are considering, that has become smaller. So what is the remedy for this? What is the remedy for this? How can you make sure that the peak at n0 is still the most salient one? Copy the same signal again. Means you are saying that you replicate the signal over and over again. Okay, good suggestion. And anybody disagrees with this idea? Why? Okay. You also said something. What's your name? Sushmita. So what was your answer? Will be good.
So, but if the signal is not ending at exactly the period, then the correlation will fall down because the time period will change.
Yes. Any other answer? Somebody raised hand. Okay. Okay, I'll tell you now. Let's say my xn is like this. 1, 2, 3. So it contains 2.5 cells. Let's call it as a cell. Cell is not a common terminology in DSP literature, but it is used in other literature like geometry. What is it called? The crystallography, where you study crystals, where they make cells. So let's call it as a cell, or one time period, or one cell. This is 1 cell, 2 cell, and 2.5 cell. Now if I repeat it, will it show peaks at n0? If I repeat this signal, will it be showing peaks at, or will the peak at n0 be equal to the peak at 0? R n0 is not same as R0, right? Because the length of the signal is not a multiple of the number of cells, or not a multiple of cells, cell size, right? Okay, so this is not a good idea. Any other idea? Any other idea?
Greater sample size. If you have greater sample size.
Let's say I gave you only this much signal. I only gave you this much signal and I want to find the time period. One idea could be.
So instead of using the, like we are creating two copies of a same signal to calculate correlation. So instead of taking full signal as a copy, take just a part of a signal and then do the correlation, and every time it will be equal, so it should not go wrong.
Okay, a good idea. So you're suggesting that when you're defining your RxXL, instead of going all the way from 0 to n minus L minus 1, you go to a smaller length, maybe some R minus or some L length, right?
But how can we know till where should be?
Yeah. Again, choosing the L will be difficult. No, you have to make sure that L is at least larger than the cell size, or so it's like.
Can we take the original signal and the shifted signal be negative of the original signal? So we will be looking for minimum instead of peaks.
You want to minimize the difference. You don't want to maximize the correlation, but you want to minimize the difference. Right? That's a very good suggestion. People do that. I will come to that in a while. I'll come to that. So we just hold it for some time. I will discuss that at length. Any other idea to make sure that the R0 and Rn0 are comparable, almost same? Normalization, right? All the time we talk about normalization. You are studying machine learning. In machine learning, you always say normalize your data, right? Normalize. How will you normalize? I have given the hint.
By dividing the number of points.
Yes, divide by the number of points. So my RxXL will be equal to summation xn plus L. N is equal to 0 to n minus 1 minus L. Just divide by n minus 1 minus L, or n minus L, or n minus L minus 1, whatever, same thing. Right? Now compute RxX at 0 and compute RxX at n0. They will be almost same. Right? Okay, so now tell me, how will this look like? This is 0. And this is n0, this is 2n0, so on. So it will have a peak here.
This transformation just scales down the whole autocorrelation signal, right?
Yeah.
So how wouldn't the same problem still persist of the peaks in between?
If I take 0, if L is 0, this is n minus 0, large number. If I increase my L to n0, this is smaller number, so the overall thing blows up. So in that way. Okay, so I will get one peak here. Then I'll get one peak here. Right? They will almost have same height. Right? One issue still remains. I may pick 2n0 instead of n0. I may not pick 0. Okay, I have avoided that problem. But I may still pick 2n0 instead of n0, right? That problem will still remain, right? Okay, just keep it in mind that this problem is there. We will discuss about it later. Okay, now let's come to who said negative? Sanreet. So Sanreet said, instead of looking at the product of the signals, look at the difference of the signals. So let's define a new measure called, what do we call it? D, difference. Squared difference. So D between signals x, x, L is equal to summation xn and xn plus L. But instead of multiplying them, I will subtract them and take their squared difference. You could take mean absolute difference also, or absolute difference or squared difference, both are fine, but we are working with squared difference. N goes from 0 to n minus L minus 1. And that's it. We don't need to normalize it because at d0 is 0, almost 0, and dn0 is also almost 0, and d2n0 is also almost 0. So how can you plot how will the D signal look like? DL look like? So let's say this is my L and this is DL. How will it look like? 0, n0 to n0.
Start from 0 and then a smaller value, smaller minima and higher.
Something like this, right? It will be large value and then it will dip.
It will be
Perfect.
perfect. Like and not some part of the value will be there with some logic.
Why? Means okay. Ideally, it will be 0 if the cells exactly match.
Part will be there.
Some part will.
Minus signal and some part will be there.
Because we are taking this difference over a truncated range, 0 to n minus L minus 1. So whatever is hanging out, we don't put them in our calculation. So yeah, okay. So ideally it will be 0, but you know, in real world you don't have exact signals, exact match. So there will be small values, but it will be very close to 0. Generally people put a threshold. Okay, if it is below this threshold, assume this is 0. Now what is the benefit here? The benefit is that if I choose some threshold, then at whatever L I see a value less than that threshold, I will just pick it as my n0. I will not go to the next to n0. I will just stop at n0 because here the value is less than a threshold, right? But now when the noise comes, means you have periodic signal but then some distortions or some noise, then you may have to do some more engineering to come to a decent solution. Okay, fine. So this term is generally called unbiased autocorrelation. Unbiased autocorrelation. This is called correlation or autocorrelation. This is unbiased autocorrelation and squared difference. All right. Now, any questions up until here? Any questions? Okay. If not, then we will change our gears and make the problem a little bit more difficult. Okay. Now, a very quick detour. Let's say I found my signal is something like this. I'm sorry for the bad drawing, but it's a periodic signal, right? And periodicity comes out to be, let's say, 30 samples. My n0 comes out to be something, 30 samples or something. This is xn. What does it mean in seconds? What is my frequency in seconds? My periodicity, this frequency in seconds. So the frequency, it's called the fundamental frequency. So, okay, let me introduce this term also. So this one you're seeing. So 1 upon n0 is the fundamental, or it corresponds to the fundamental frequency. Fundamental frequency of the signal, right? Okay, what is the fundamental frequency of this signal in hertz? Or what is the time period of this signal in seconds? I'm not saying in samples, but units should be seconds. How will you find that out? Unit sampling rate. Okay, let's say sampling rate is fs. So sampling rate is fs. Then what is my f naught? Likewise t naught. Huh? Okay, so f naught is fs upon n naught. And what is t naught? Seconds, hertz. Right? Per second means hertz. Okay. Is this clear? Do you need any justification for this? Is this clear? Okay. Can you prove this? How will you prove this? How will you prove this? Huh? Obvious. Yeah, actually, yeah, it's obvious. It's unitary method, no? That distance between two samples is 1 upon fs. Distance between n naught samples is n naught upon fs. Simple unitary method, right? Which we learnt in our which class? I don't know. Which standard? Yeah. Okay. Then this was a just small detour. So if you see, you record your audio, you plot it on Praat or any other tool, Python, and then you found some periodicity n naught, then you should not find it difficult to tell me the frequency in hertz or a time period in seconds. Okay, so now let's make the problem a little bit more difficult. I have a signal which is sum of sinusoids, my x. So let's say I have an xn. This is equal to a naught cos 2 pi 5n upon 32 plus a naught cos 2 pi 10n upon 32. Right? This is a periodic signal, right? If I just give you the signal xn, I don't tell you the expression cos plus cos, etc. And I ask you, can you find the periodicity of this signal, which means this 5. Can you tell me the period of this signal? How will you tell? So one way to tell periodicity is, okay, as we discussed, take the autocorrelation, do all that. That is all good. Another way to do the same thing is, if I multiply xn with, let's say, cos 2 pi 5n upon 32, and I take sum over n equal to 0 to 32, 31, okay. What will this term be? What will this term be equal to? Can you find out analytically what is this term equal to? Okay. Forget the physical interpretation, just look at this analytical form, try to compute this value. What is xn into cos 2 pi 5n upon 32? Summation n equal to 0 to 31. What is this sum equal to? You will need your notebook to find that out. It's not very easy, it's not obvious, but you may need some trigonometric identities. So one identity which you may need is cos A into cos B is equal to yes. So 2 cos A cos B is equal to cos A plus B plus cos A minus B. 2 cos A cos B is equal to cos A plus B plus cos A minus B. Simple trigonometric identity. Using this, find out this formula. Done? Done? A naught into pi. Okay, that's one answer. Anybody has any other answer? Any other answer? Huh? Okay. Another answer is A naught into 16. Any other answer? Okay. I will. Pardon? Okay. So let's see. First term is A naught into cos into cos. Okay. So let's say A naught. So this is A1. I'm sorry. This was A1. Okay, but anyways, even if you're done with A naught, I have no problem. A naught. Now this cos into this cos, so it becomes cos of 5 plus 5n. So how much? 10n. So 2 pi by 32 10n plus cos A minus B, that is cos 0. Cos 0 is 1. Okay, divided by 2 plus A naught by 2 into, sorry, A1 by 2 into cos of 2 pi by 32. What is that? 5 and 10, So 10 plus 5, 15n plus cos 10 minus 5, so 5n. Now there is a summation outside, which is from n equal to 0 to 31. Look at the first term, cos 2 pi by 32 into 10n. When you sum it over from n 0 to n 31, what will be the summation? So you have from 0 to 31. So when you reach about 31 or 32, you will have covered almost 10 cycles of the cos, right? So it's like whatever number, I'm not counting. Something like this, 10 cycles. Right? And you sum over it, what is the answer? Almost 0, right? So this term will become almost 0. What about 15n? 15 cycles, so almost 0. 5n, 5 cycles, almost 0. Which term remains? So what is the sum? A0 by 2 into sum over 1 31 times, so 32 times, so it becomes 30. So it becomes 16 A0. Right? Clear? So, okay, now let's take this, look at this value. Instead of 5, try 6. What is the final outcome? 0. Why? Because cos A plus B, let's say 5 plus, let's say this is 6, 5 plus 6 is 11. That will also means 11 cycles, 0. And 6 minus 5 is 1 cycle, that is also 0. Any other value you take other than 5, it will be 0. But there is one more value which will not give 0. 10. Then 10 and 10 will match, and again you will get something. So now, which means that this term, this whatever this expression is, it will also show peaks at the fundamental frequency 5 in this case. It will show peaks at 5. What about 0? If this thing is 0, what will happen? If this yellow thing is 0, what will be the outcome? 0, again 0. So it doesn't have a peak at 0, right? No peak at 0. 0 is also flat. It gets peak at 5 and 10 only. Here the magnitude is A0, 32 by 2, 16 A0. Here it will be 16 A1. So depending on A0 and A1, you will get the relative peaks. This is a very good method to find periodicity of a signal, right? You probe the signal with multiple sinusoids, and whichever sinusoid matches, it will peak. Whichever does not match, it will be suppressed. So kind of you tune your sinusoid with the signal, right? So this can inspire you to think about Fourier transforms. What is Fourier transform? You have a signal and you are probing it with multiple sinusoids, or sinusoids with multiple frequency. And whatever outcomes you are getting, those are your Fourier transforms. Is that understanding of Fourier transform clear? So let's talk about then Fourier transform. Discrete Fourier transform. My x of n is something. My x of k is equal to, I will probe my x of n with some minus j 2 pi by capital N k times n. I am probing it with what frequency? K frequency. Means okay, it's okay. I will okay basically. So this is k thing, and whichever k matches x of n, there I will get a peak, and whichever k does not match, I will get a flat 0 value. Right. So that's the idea, how we are probing or how we are estimating the fundamental frequency of our signal with the help of Fourier transforms. This is called a discrete Fourier transform. Happy? Everything is clear, intuitive, easy to understand. Anybody is lost? Raise your hand. We'll pick you up. Anybody is feeling lost? Okay, good. Now, tell me if my x of n is a sinusoid, let's say, if let's say I know my capital N. Let's why to assume that they are same. Let's make it more general. Where f is basically less than 1. Right? Tell me what will be the xk. You are probing it with some frequencies. Oh, can you see instead of cos I have introduced suddenly I have introduced exponential of something. Is that confusing? Suddenly where did this exponential come from? No? Okay. Yeah, let me see if I have some simpler understanding. So yeah. So you can replace exponential also with a cos. You can say cos of 2 pi k n upon capital N, but then the calculations become little messy because multiplication, if you want to multiply two cosine values, you have to use trigonometric identities. But if you have everything in terms of exponential, you don't need trigonometric identities because you can, product is simply a sum of exponents, right? That's why we use exponential, because just to make our analytical analysis simpler. Okay, so tell me what is xk. Roughly, I don't want exact calculation. Just roughly, you can tell how will it look like. It will peak at what values? At f. At f. Huh? K is an integer going from 0 to n minus 1. K goes from pardon? If my k becomes larger than capital N, what happens? Starts repeating. Yeah, it's a periodic thing, no? Because exponential of 2 pi by n, this thing is a periodic function. So if I make my k greater than capital N, it will be same as n minus or k minus capital N because of periodicity. Right. So therefore, we only are interested in k equal to 0 to capital N minus 1. Okay, now tell me how will the xk look like? Where will it peak? K equal to nf. nf. Okay, any other answer? No? How did you find out?
So we like xn in exponential form and then see where it goes to, like the power. So it's f minus k upon n.
Yes, very good. So basically, the peak will occur when k upon capital N will be equal to f. Right? Then only the difference will become 0 and things like that. No? Okay. Any other place? So basically k is equal to n times f. So you can say you round it off. Round it off basically. Right. Where else? will the peak occur? Is this the only place where the peak will occur, or any other place? Huh? Yes, so peak will occur at this k equal to nf, then k equal to 2nf. Why? N minus nf. Very good. Okay, let's compute the value, then you can understand. So my x of k is equal to summation x. Xn is cos. How do you multiply cos with exponential? Yeah, you can write cos also as sum of exponential. Let us do that. E to the power j 2 pi fn plus e to the power minus j 2 pi fn upon 2 into e to the power, what was that, minus j 2 pi kn upon capital N. Right? So the whole thing will become non-zero when my f is equal to k upon n and when my minus f is equal to k upon n. So basically it means when my f minus k upon n is equal to 0, or when minus f minus k upon n is equal to 0 or capital N, whatever. Right? If it's equal to capital N, then okay, I think I have to do some more. I will ignore the first term. The second term is e to the power minus j 2 pi n f plus k upon, right? This term is this. Right? So if this term becomes equal to divided by capital N, it's also there. No, it's not there. Then if this term becomes equal to 1, right? If this term becomes equal to 1, what will happen? E to the power minus j 2 pi n. What is that? It's always 1. E to the power minus j 2 pi, e to the minus j 4 pi, e to the minus j 6 pi, 8 pi, they're always 1. Right? So this is the case. So when f is equal to, so what do we get from here? F is equal to how much? N minus k, right? N minus k. Did I do some mistake? Upon n. Right? N minus k upon n. So both are the answers. So from here you get f is equal to k by n. Here you get n minus k upon n. Pardon?
So why do we take minus in Fourier transform? E raised to a minus?
Just a convention. It's a convention. We'll discuss that whether you take minus or not, it's the same thing. But by convention, you take minus and all the formula, all the properties are derived from this convention. If you change this convention, then all the formulas you have to derive again and memorize those things. Okay, so now since we have motivated the reason why we are using DFT, let me summarize what is DFT. It's called discrete Fourier transform. X of k is if I give you x of k, can you find out x of n? There is some normalizing term. Let me check. 1 by n, huh? Okay, 1 upon n. Yes, thank you. Prove it. Prove this. That if x of k is x of n this into this, prove that x of n is this. It is uniquely determined. X of n is known uniquely and it is this value. Can you prove this? Okay, take it as a homework. Last time I gave some homework, right? What was that? Huh?
First response property quality. Any other response.
Put a simple function, then any other function can be.
Oh, yes. Could you do that? Could you do that? Anybody who needs help? Anybody who could not do it and you want this to be discussed in the class? Oh, okay, then we'll put it in the exam. Anybody who wants help, don't feel shy. Just raise your hand and ask questions. It's a good thing to ask questions. Okay, fine. So you can. Pardon? In that question? Okay. So basically, after this, this proof is very easy. How will you prove this? Just start from the right hand side. You will arrive at the left hand side, right? Start from the right hand side, and you will arrive at the left hand side. What property will you use? The same property that if you probe properly, then things will summation of e to the power j 2 pi something, whatever it is. Okay. Equal to 0 if f is not equal to 0. Basically, that's the property. That's it. Using this property, you can find out you can prove this, right? Summation over exponential j 2 pi k upon n f is equal to 0 if f is not equal to 0, right? 0 are basically a multiple of n. If f is not an integer multiple of capital N, then this thing is equal to 0 always. That's it. Using this property, you can prove that. Okay. Now let me see if I remember the question which was asked last time. What was the question? Oh, this was the question in LTI systems. Yeah, this was the question. Given t delta n, we can know t xn for any xn. That is what the question was. And how do you prove it? To prove it, take any general t xn, express it in terms of t delta n, right? Take any general t xn, and express it in terms of T delta n. And what can help you? The LTI properties can help you. Let's do that. So solution or whatever, T of xn, right? So this is equal to what? Can I say, what is my xn? Xn is xn is basically all these signals, no? All these values at 0, 1, 2, 3, 4, right? That's the signal xn. Can I write it as this? I can say my x of n. I want to write xn in terms of delta n because I only know T delta n. I don't know t of xn. I know T delta n. So let me express x in terms of delta. That's the obvious thing I would like to do. So my xn how can I write it as in terms of delta n? Summation x basically minus infinity plus infinity. Can I write it like this? All of you agree that I can write xn in terms of delta in this way? So here xm is just a coefficient. It's the height of this this signal, right? So this xm is just the heights. These are just the heights of these signals, just some constant value. Now let's do let's see T of is equal to T of this whole thing, right? But because of the linearity property, I know T of a1x plus a2x is equal to a times T of x plus a2 times T of x, right? So here what is x here? Delta n, because n is my variable, right? M is just a dummy variable. So I can say this is equal to summation m equal to minus infinity to infinity x of m T of delta and minus m, right? Can I express T of delta n minus m in terms of T of delta n? How will I do that? So again I will say T of the nth component because of time invariance property, what was time invariance property? That T of delta n minus m n is equal to T of delta n n minus m. That was a time invariance property, right? By that I can take out my n minus m and I know T delta n. What is it? It is given to me. So that's how I arrive at this form. So now let's let delta n or T of delta n nth component is equal, let's call it as h of n, then T of xn agreed? So in this way, if I know T of delta n as h of n, then I can compute T for transformation of any xn. And this form, the right hand side, is very famous form. It became famous because of LTI systems, and this form is called an operation which is known as convolution operation. Convolution has no other meaning other than LTI systems. Means apart from LTI systems, convolution has had no meanings. But nowadays, convolution has become very popular again because of CNNs, convolutional neural networks, right? So, but the underlying basis is linear time invariant systems, right? So some people say signal processing is the foundation of deep learning. So you can see that here. And let's talk about some properties of convolution. So convolution is commutative, which means x of n is written as h of n. So this thing is equal to this. In short form, it is written in this way. X of n convolved with h of n. This means that xm hn minus m summation over m. So commutativity means that this thing is equal to h of n convolved with x of n. Right? Clear? Can you prove this? Plug in the values. So instead of saying xm hn minus m, you say hm x n minus m and prove that both are same. Just change of variables and you can prove it. It's very easy. Then there are some other properties, like I will just list them out so that this is called commutativity. Then distribution over addition. It means x of n convolved with h1 of n plus h2 of n is equal to xn convolved with h1 of n plus xn convolved with h2 of n. And then you have associativity, which means x of n convolved with h1 of n convolved with h2 of n. You can do it in two ways. Either first do this and then do that, or first do this and then do that, right? And both are same. That's the meaning of associativity. Whether you do x and h1 first and that thing with h2 later, or you do h1 and h2 first and that thing with x later, both are same. Another property is stability. It says that if my h of n if my h of n is absolute summable, then my system is stable, which means if my input is finite input, it's bounded input, then my output will always be bounded. If my hn is absolute summable, absolutely summable, or whatever. If my hn is absolutely summable, then my system is Bibo stable, which means if my input is bounded, output will always be bounded. Okay. Yeah, that's it. This was all convolution thing which we could not cover last time. Any questions at this point? No? Then I'll go to Pratt. How many of you were able to install Praat? Okay, good. Could you play with it? Could you record some sounds and analyze those sounds? Do you have any questions about those? I wanted to discuss Praat today, but it seems this lecture took so much of time.
Sir, another one you said SOX. You could not do
Huh?
SOX, sound exchange.
SOX,
I
SOX.
was unable to actually
Install. You are using Windows or Linux? Windows.
I tried in Python as well.
I don't know Windows because I don't know if SOX exists in Windows. I don't know. In Python it is there. In
On that website it was there. There was exe file. And after installation
Okay.
it actually opens and goes in a moment.
Okay, I would suggest use Linux. If you can install Linux on your computer, that will be better because Windows is not very good for programming. Some people use it, but I find it a little inconvenient. So, some things which work very well in okay, now let's say Praat. I have some exercises, but okay. Praat has a functionality, has some inbuilt functionalities. Let's see them. Read from file or record. Okay, I can zoom in. That's how it looks like. You can see it's a periodic signal. I can zoom in further. You can see it's a periodic signal, right? But it's not simply sinusoid. It is periodic, but it has got some other structure, not sinusoid. How will you find its time period? How will you find its time period? Quickly look at this figure and tell me the time period. How will you find a time period? Competition. How I would do is, I will pick one peak here, note down its time period, and this peak. So you can see it is 0.007788 seconds, which means it is 128 hertz. The frequency here was 128 hertz, right? There are many ways to calculate, but given this tool, this is the fastest I could do. Now look at this blue line here. What does it say? 127.6 hertz, right? So this blue thing is actually telling the frequency, the fundamental frequency of my sound. If I am singing, if I am speaking at this fundamental frequency, this blue curve tells me. And how do I adjust the blue curve? There is an option called pitch. I can say show pitch or I can turn it off. So see this show pitch thing? I say yes. Now it has appeared. The blue curve has appeared. Right? Is this clear? Now let's do some music. New file. Okay. What did I sing? And what is the difference between these three signals? Signals are different, but can you find some very crisp property which has changed? Very crisp, when I say crisp, it means you want to find the minimal information from that signal which correlates with that property. Right? I repeat. You want to find the minimal information from that signal which correlates with that property. Ideally, it could be a scalar value. One scalar value which you can derive from a signal which correlates with this musical property. What is the musical property? That the pitch is higher or lower, right? When I say this is sa re ga, let's say, then sa has a lower pitch, re has little higher pitch, ga has little higher pitch. Right? So what is that property in the signal which correlates with this pitch perceptual? What is that property? Pitch. See, here my pitch was 132. Right? If you can zoom in, you can actually see it's 132. You can zoom in. Oops. Select. Let's take this peak and this peak. About 134.7. Because of my selection may not be very perfect. If you take the autocorrelation thing, there you take a long signal, then you can very precisely find out. So this is roughly 134, so actually it is 132.6 hertz. Right? And when I come here, pitch is 148.7. Here 166.4. So when I say music, when I say different notes, they have different frequency values, you can see here. Okay, now since time is over, I will give one homework. Now, when you go home, go to your room, record different kinds of sounds and see what is different there. I'll give an example. If I say o, e, u, a, what is different in these sounds? Frequency? No, it's the same. Fundamental frequency is the same. The fundamental frequency is the same. What has changed? So go back home, record these sounds, and do check on your own what has changed. Right? Okay, now another thing which I would like to say is, when I say what has changed? So can you also do this experiment and see what property of signal has changed here? Right? Try different sounds and see which property has changed. And can we find some statistical measures or some measures in the signal which can correlate with that perceptual property? Right? So we'll discuss that in the next class. Thank you.